Radioactive decay. Radioactive decay is spontaneous and random disintegration of unstable nucleus into more stable configuration by emitting alpha, beta, or gamma radiation, with slight or no change in the mass of the nucleus. It's important to note that radioactive decay is random, and what they meant by random is that it occurs spontaneously and not affected by external conditions such as temperature and pressure. The rate of decay is known to be directly proportional to the number of radioactive atoms. Hence, if you have a larger number of radioactive atoms, the rate of decay will increase proportionally. Let's now take a look at the 3 types of radioactive decay. The first type involves the emission of an alpha particle. The alpha particle comprises a helium nucleus, and in the nucleus, you will have 2 protons and 2 neutrons. Therefore, it has a charge of plus 2e, where E is equal to 1.6 times 10 to the power minus 19 coulomb, and the mass of an alpha particle is 4u, where u is the unified atomic mass constant. And the typical speed of the alpha particle is in the region of 10% of the speed of light. Alpha particle, which has substantial mass and therefore substantial momentum, would have negligible wavelength. Therefore, alpha particle behaves more like a particle. Alpha particle could be stopped by 0.5 millimeter of your paper. Beta emission. In beta emission, a beta particle will be emitted, and beta particle is an electron, so it has a charge of negative E, and the mass of an electron is given as 9.11 times 10 to the power minus 31 kilogram. The speed typically is about 90% of the speed of light, and beta particle, like alpha particle, behave more like a particle. It could be stopped by a few millimeters of aluminum sheet. Gamma radiation. Gamma radiation is part of an electromagnetic wave with wavelength less than 1 picometer, typically in the range of 10 to the power of minus 11 to 10 to the power of minus 15 meter in terms of its wavelength. Therefore, it does not have a charge. Its mass is approximately 0, and it travels at the speed of light. And gamma radiation can be absorbed by lead. With the understanding of the charge of alpha particle, which is positively charged, beta particle, which is negatively charged, and gamma radiation, which do not have any charge, when they pass through an electric field, the gamma radiation will pass through undeviated since it does not have a charge. Alpha particle will tend towards the negatively charged plate, but you will deflect it at a smaller angle relative to your beta particle. Reason being, beta particle has mass significantly lower than that of your alpha particle. And beta particle will be deflected in the opposite direction since beta particle is negatively charged. When gamma radiation passes through the magnetic field, given that gamma does not have any charge, it will pass through again undeviated. In the case of alpha particle, its velocity will be indicated in this direction, and magnetic field is coming out of the paper. So therefore, because of this, a magnetic force will act on the alpha particle in this direction, forcing the alpha particle to undertake circular motion and hence traveling a circular path as drawn here. In the case of the beta particle, which is negatively charged, the current would be in the opposite direction, despite the velocity going from left to right. Since the current is in the opposite direction, as the direction of travel of the beta particle, the magnetic force will be acting in this direction. Therefore, the beta particle will be deflected in the opposite direction and undertake a circular path. And since the mass of the electron is significantly lower than the mass of the alpha particle, radius of the circular path undertaken by the beta particle will be smaller than that of alpha particle. Let's now take a look at the equation of alpha, beta, and gamma decay. In the case of alpha decay, the parent nuclei will be converted to the daughter nuclei, emitting the alpha particle, or otherwise the helium nuclei. And the number represented by A is termed as the mass number, which comprises the proton plus the neutron. In short, it comprises the number of nucleons in the nuclei, while the number represented as Z represents the number of protons in the nucleus. Hence, in the alpha decay, the mass number or the nucleon number will decrease by 4, while the atomic number or the number of protons will decrease by 2. Let's now take a look at beta decay. There are 2 types of beta decay. When the number of neutron is larger than proton, the neutron can be converted to a proton and in the process emits an electron. This is represented by the equations as indicated here. And as you can see, in the case of a neutron, the mass number is 1, while the proton number is 0. When it is converted to a proton, an electron will be emitted alongside it. In order for the mass number of the proton plus the electron, which in this case 1 plus 0, to give you 1. And in the case of the proton number, where the proton number of your proton is 1 and the proton number of an electron is -1, when both add together, they will give the proton number of your neutron, which is 0. An example of the nuclear reaction is with iodine with a mass number of 131 and a proton number of 53, which produce xenon with a mass number of 131 as well, but the proton number is now 54. And alongside it, an electron or a beta particle has been emitted. It is also important to note that as part of the emission, there will be an antiparticle termed as anti-neutrino that has been emitted as well. This antiparticle does not have any mass, neither does it have any charge as well. And so therefore, even if we were to feature in the equation, it will be represented as such. How does scientists know that an antiparticle is being emitted during beta decay? The reason is because in the beta decay, we know that using the conservation of momentum, that momentum ought to be conserved before and after the nuclear reactions. So in this case, if a parent nuclei is at rest and after beta emission, say for example, the daughter nuclei were to move in this direction, then we can conclude to say that the beta particle must move directly in the opposite direction. However, evidence has indicated otherwise, while the direction of the velocity of the beta particle is not opposite to the velocity of your daughter nuclei. So hence, if the beta particle is emitted in this direction, we know that in order for momentum still to be conserved, there must now be an antiparticle that must be emitted in the direction above, in order to account for the downward momentum of the beta particle. And scientists also observe that the beta particles that's been emitted has a range of kinetic energies that further provide evidence that antiparticle, and specifically in this case, anti-neutrino, has been emitted during beta decay. The second type of beta emission occurs when the number of protons in the nucleus is larger than the number of neutrons. In this case, a proton would now be converted to a neutron, and alongside it, a positron is produced. Positron is exactly identical to an electron, except that it has a positive E charge instead of the case of a new electron, which has a negative E charge. And hence, in this nuclear reaction, carbon, which has a mass number of 11 and a proton number of 6, undergo beta emission to produce a boron with the same mass number of 11, but the proton number has decreased from 6 to 5. In the process, a positron has been emitted. Gamma decay. During gamma decay, the unstable radioactive nuclide, which is of a higher energy level, stabilizes itself and hence its energy level drop. In the process of the decrease in its energy level, gamma radiation is emitted, governed by the decrease in energy as equal to HF, and which is actually equal to Hc over lambda. As highlighted earlier, the wavelength of gamma radiation range in 10 to the power of -11 to 10 to the power of -15 meter. Since gamma radiation does not have any charge or mass, in the balancing of the nuclear reactions, the mass number and the proton number does not change, and we can indicate gamma as such. Therefore, in conclusion, this is a summary. So alpha particle is a helium nuclei, and it has only a specific speed. Beta particle has a mass, has significantly lower mass than the alpha particle. It has a continuous range of kinetic energy due to the fact that anti-neutrino is produced alongside it during beta decay. While in the case of gamma radiation, it is no mass, it is just a wave, and it travels at the speed of light. And finally, we want to add that in the case of your neutrino, it does not have any charge or mass, and it also has a continuous range of speed.